Ingamana, Ingarea, Ro Rakatidama, Tanakoto, Tanakoto, Tanakoto. Norera, Ko Waio, Ko Harleen Hain Takawingawa, Ko Te Tumuakio Te Whare Wanaka o Atago Aho. Namihi Nui Kiakoto, Norera, Tanakoto, Tanakoto, Tanatato Katoa. Welcome, everyone. My name is Harleen Hain, and I have the privilege of being the Vice Chancellor here at the University of Otago. And it is my great pleasure to be the first person to welcome you to this inaugural professorial lecture. As you're all aware, these lectures are really a time of huge celebration for the university, and it is fantastic to see so many people here taking part in the celebration of James's amazing career. On behalf of the university, I would like to begin by extending a particularly warm welcome to members of James' family who are here with us in the audience this evening. His mum and dad, Linda and Grant, are here, his wife, Helen, and their children, Josh and Abby. Thank you so much for coming. The presence of family members is yet another clear indication about the importance of this evening. Now, in addition to these very special members of our audience, as I look out on the people gathered here, I see staff and students from around the university, as well as members of the general Dunedin public, and a special welcome to our Chancellor, Dr. Royden Somerville, who is also a regular attendee of these incredibly important events. To each and every one of you, no mai, haramai, welcome. Now, in setting the scene for tonight's event, I think it's really important that we all remind ourselves that the path to professor here at the University of Otago is not an easy one. In order to achieve this promotion, the individual must demonstrate excellence in teaching, in research, and in service to the university and the wider community. Now, as you will learn through his lecture this evening, James is an inspirational and motivating classroom teacher. He is also a very sought-after and popular postgraduate supervisor. In addition to his teaching ability, James is also an award-winning, highly cited, and very well-funded scientist. And tonight, we will all have the opportunity to learn more about his groundbreaking research in the area of synthetic chemistry. And last, but certainly not least, James has provided exceptional service to the university and to the wider academic community. So James, on behalf of the university, it gives me great pleasure to congratulate you on your very well-earned promotion to professor. And I will now call on the Pro-Vice Chancellor of Sciences, Professor Richard Barker, to tell us just a little bit more about James's academic journey to professorship. Norera, Tanakoto, Tanakoto, Tanatato Katoa.
Vice-Chancellor, tēnā koe. Deputy Vice-Chancellor, tēnā koe. Professor Crowley, tēnā koe. Professor Gordon, tēnā koe. Friends and colleagues, tēnā koutou, tēnā koutou, tēnā koutou katoa. It is my great pleasure to introduce our speaker tonight, Professor James Crowley, to give his inaugural professorial lecture at the University of Otago. As indicated by the Vice-Chancellor, Professor Crowley is one of our newer professors at the university, receiving a well-deserved promotion to the position in February earlier this year. Born in Wellington, Professor Crowley has a keen interest in Lego, it appears. So from the building blocks of childhood and adulthood, as I understand it, to the building blocks of chemistry. This began with a BSc Honours earned from Victoria University before going on to receive a Master's from Victoria and then to a PhD from the University of Chicago. While at Chicago, he won the Joan Shiu Award for Student Service in the Department of Chemistry, and awards will be a theme that runs through this introduction. After completing his PhD, he then crossed the ditch, taking up a postdoctoral fellowship at the University of Edinburgh, followed by a second one at the University of Edinburgh, but this one with the title of the Ramsay Memorial Postdoctoral Fellowship. This is the most prestigious UK postdoctoral fellowship available to chemists from the Commonwealth. At the end of his time in the UK, Professor Crowley joined the University of Otago as a lecturer in 2008 and began a speedy journey through the academic ranks, seeing him awarded promotion to full professor just 10 years later. Professor Crowley is a synthetic chemist, which I think means he makes stuff. In particular, he and his research group design and synthesise new functional molecules that have uses as antibacterial and anti-cancer agents. He also works on a range of solutions to problems in drug delivery and catalysis applications, which I think means making things work faster or better. Professor Crowley has received significant grant support along the way, including from the Marsden Fund from the New Zealand Royal Society twice, the Otago Medical Research Foundation and the Royal Society. Through his leadership, he has won a number of awards, including the New Zealand Institute of Chemistry Maurice Wilkins Centre Prize for Chemical Science in 2017. This prize is awarded annually to the top chemist in New Zealand. He won the Royal Australian Chemical Institute Organometallic Chemistry Award in 2015. This is awarded annually to an early career organometallic chemist in Australia or New Zealand. Professor Crowley is the first and only New Zealander to have received that award. The Chemical Society of Japan Asian International Distinguished Lectureship Award was won in 2015, and in 2013 the Royal Society of Chemistry and the New Zealand Institute of Chemistry Easterfield Medal. Professor Crowley was made Fellow of the New Zealand Institute of Chemistry in 2014 and then a Fellow of the Royal Society of Chemistry in 2016. He's an Associate Investigator in the McDiarmid Institute and is a member of the New Zealand Institute of Chemistry. National Council has been for 7 years, and he is the current President of that institute. In addition to his research, he is also an outstanding teacher at both undergraduate and postgraduate level. He has every reason to be proud of his postgraduate supervision record: 16 PhDs, 5 master's students, 15 honours students in just 10 years is outstanding. In 2015 and then again in 2017, he was a finalist in the Otago University Students Association Supervisor of the Year Awards. In addition to time spent as an academic, Professor Crowley is also quite the coach. He was the assistant coach of the Under-7 Whites Southern Rugby Club, which he coached to Ripper Rugby Team of the Year, assistant coach and coach of the St Clair Rippers T-ball team, assistant coach Team Watson Grade 4 Albion Junior Cricket, assistant coach Strikers Grade 9 and then Grade 10 with Melchester Rovers. Tonight, Professor Crowley is going to describe his personal and academic journey and enlighten us on his research into molecular scale construction. Please join me in welcoming Professor James Crowley.
It's working? Fantastic. It's a bit worrying to be standing up front here because I must admit, when I started out a long time ago as an undergraduate, I didn't think I'd ever end up as a professor, so it's nice and it's yeah, something to live up to, I guess. So my talk's going to outline a little bit about what we do in my group, and as people have said, synthetic chemists, we make stuff, and this is a quote from a long time ago when I started at Otago, and I was on the NZIC, the New Zealand Institute of Chemistry Otago branch, and a new PhD student and I had both joined the branch, and the student said to me, "Oh, what is it that you do?" And I said, "Oh, I'm a synthetic chemist," and they, "Oh, so you just make stuff," in a kind of, I thought, derogatory kind of way. And I think it's a misunderstanding that actually making stuff is not that easy and it's kind of important. And so I start with this slide a lot to try and get across the importance of synthetic chemistry. The quote there is not mine. As it says, George Hammond said, "The most fundamental and lasting objective of synthesis is not the production of new compounds, but the production of new properties." And so that's what we try to do in my group. And so you can see from the slide that there's a lot of areas where, as a chemist, you can contribute to. You can contribute to biology, and we have some excellent collaborators in the biological departments around the university. You can contribute to materials, so all your iPhones and computers are made up of synthetic molecules that synthetic chemists built. Obviously you needed physicists and engineers and other people to help out, but chemistry is central to all of that. And so that's what we do, and there are many things that we can continue to contribute to. Catalysis and energy are both very important current problems in the world, and so that's where synthetic chemists can be useful, and that's part of what we spend our time doing. And Richard already stole my thunder, and my children who are up there helped me make this. And this is perhaps how I ended up as a chemist, maybe not, but I'm lucky that my parents, when I was little, bought me some Lego. Maybe the previous generation of synthetic chemists, it was Meccano, but in my generation it was Lego. And so I had a lot of Lego sets when I was little. I didn't realise that would turn me into a synthetic chemist, but apparently it did. And basically, synthetic chemistry can be thought of as like Lego. You can use building blocks to build up new materials. Now, of course, that's Lego, and there's, I think, the guy from the Lego movie whose name escapes me, and he's building something with that Lego. And that's basically what we do, but we do it with atoms. And so we're using atoms as building blocks to make new materials. So that's our Lego building block set. This is the periodic table, and of course, it's the International Year of the Periodic Table, and so there's now 118 elements in the periodic table. Many of the ones right down the bottom are a bit useless to synthetic chemists because they don't last long enough, but further up the top, particularly that one in the middle with the C on it, and the one that I'm about to circle now, carbon is what most people think of as the most important element for synthetic chemistry. And so synthetic chemistry really came out of organic chemistry, and that's the chemistry of carbon. And carbon only has 4 electrons. It has 3 different kinds of geometries, really, but it's a pretty versatile and amazing element. Most of us are made up of carbon-containing molecules, and so organic chemistry particularly was the foundation of synthetic chemistry, and still remains the major part of it. And so we have a fantastic chemistry department with a number of organic chemists, and they continue to build brilliant molecules using just carbon and these elements around the side of carbon mostly. And the reason that they do that even now is because biological molecules are mostly made of carbon, and a lot of the drug molecules that we make come from nature, and so those organic chemists in my department often try and make these natural products and look at them for their drug interactions. Sadly, I'm not an organic chemist, so we can't just use carbon, or at least my group doesn't just use carbon. We use a bit more of the periodic table, probably that much, although even that's an overestimate. And so we try and tie in organic chemistry and coordination chemistry, or the chemistry of the D block, which is that bit that's circled, transition metals and the like, to build more complex molecules. Now, unlike natural products, a lot of these molecules, we don't know what the properties will be when we start out. We try and design in interesting properties, but we're not always successful, and you'll see that as I talk about some of our systems today. So how did I get here? I got told I had to say this, and so this is how I ended up, at least an academic at Otago. As I said, well, Richard said, I was born, well, not in Wellington, but in Lower Hutt, so pretty close. And it's basically Wellington, but cooler. I started school in Lower Hutt, or in Taita, a long, long time ago. I'm not going to say when, but I was lucky. My dad, who's for some reason taking a photo of me at this very point in time, was in the army, and so we moved around a bit, and I lived in Singapore, and then Wairau, great place, Wairau, good for skiing, and then Palmerston North, and then we moved back to Wellington. So I had lucky to be in a number of different schools, a lot of different teachers, all of whom are pretty inspiring. We moved back to Wellington, and I went to college at Wellington College, and that's probably where I got into chemistry. I had a really good chemistry teacher at Wellington College, and they encouraged me to do chemistry at university. And so I went on to undergraduate at Victoria, Victoria, the University of Wellington. Despite them trying to change the name, I'm not going to. I did my undergraduate there. My dad wouldn't let me just do chemistry. He thought that there was no way that you could end up with a job if you were a chemist. So he insisted that I do first-year law, which I did. Hated every minute of it, but I did get into second-year law and then decided that it really wasn't for me and stuck with the chemistry. And then, of course, I had to make a career out of chemistry, and I still didn't really do that as an undergraduate. I got to third-year chemistry, and I got inspired by one of my lecturers, or Professor Jim Johnston. He was, I think his actual title was Professor of Industrial Chemistry, and it's definitely not what I do, but he was interested in trying to take silicate materials from geothermal fields and find uses for them. And I was very lucky I got to do a third year project with Jim, and that got me interested in research. It also made me realise I didn't want to do that for research, but it got me interested in research. And so as a fourth year, I stayed on, I did honours, and I did that with this guy here, Dr. David Weatherburn, and he's a coordination chemist, which is how I ended up, I guess, an inorganic coordination chemist that I am now. So I worked in his research group for a year, and then I decided I'd quite like to do a PhD, but I didn't want to do it at Victoria. So I started looking for PhD overseas, and then at the same time did a master's with David. And then David, bless him, decided that he'd take a sabbatical and left me all alone in my master's, and so that's why there's another face on that slide there, Professor John Spencer, sorry. He helped me out in my master's and allowed me to finish that, and then I, somewhat fortuitously, having met this guy here, Bryce Bosnich, at a conference while I was doing my master's, got a PhD scholarship to go to the University of Chicago. And so that's how I ended up doing a PhD all the way on the other side of the world, going from Wellington, which was nice and safe and interesting, over to here to Chicago, which was completely different kettle of fish. And I see David Moran up there, and he knows what I'm talking about. The American PhD system is not like the New Zealand one. It's, well, minimum 5 years, and there's coursework, and that part was okay, but also there's candidacy exams and various other hurdles along the way, and it was a bit of a change of pace from New Zealand to Chicago when I got there. Also, there was an expectation, although luckily not in my group, Boz, although he was a little bit crazy, he wasn't completely crazy, and he only expected me to work 6 days a week, whereas most other groups expect you to work 7 days a week. Somehow I survived my time in Chicago and ended up moving to the UK and doing a postdoc with Professor Dave Lee, who's shown there. And at the time, Dave was in Edinburgh, and that was great. We spent 2.5 years there doing my postdoc with him, and because of them, I ended up getting this job here at Otago, which was very nice. And basically what I do now is a conglomeration of things that they taught me along the way. So what my research group does now is shown here. We tinker with a lot of different areas, and we have a lot of collaborators who make this possible. It says on the top, synthetic inorganic supramolecular chemistry, so not organic chemistry, but organic chemistry plus metal ions and plus supramolecular chemistry, which is non-covalent. And we try and apply it in different areas. We try and make macrocycles, and we do that so that we can make these interlocked architectures, and that's what I learnt when I was in Dave Lee's group. That's what his research group does. And they're interesting to try and make molecular machines based on biological molecular machines, but I won't touch on that today. The other things that we do a lot of is these self-assembled cages. Here's one here, but I'll discuss later. And catalysis and photoactive materials, and that's all. We make the materials, and then we study the properties through collaboration. And then the last thing, and this is something that I started when I got to Otago, we're trying to apply some of our molecules in medicine. Now, we haven't been particularly successful, but we're working towards developing new kinds of drugs or new drug delivery agents. And so that's what the group does. And a lot of it is centered around this reaction here, which I'll talk about in a second, but it's a click reaction. And the reason that we like that is because it's easy to do. Synthetic chemistry, if you want to make new functional molecules, you want to be able to make them easily and change them easily, and that's what the click chemistry allows us to do. So because I would forget normally and get to the end to be rushed and panicked, I'm going to thank all my collaborators who've helped us out over the years, and more importantly, all of the students. Now, as Richard said, I've been real lucky. I've had a lot of students and a lot of very good students, and they're all listed here. I'm not going to name them all, but these ones at the top, they've all worked in my group either as honours students or master's students, and I've been really lucky to have good honours and good master's students. Those are the ones who haven't gone on to PhDs. The ones below, this bunch here, are all PhD students, either in the group at the moment or past PhD students. Many of them started out as honours students. Most of our students come from Otago. We've had a few international students, but we've been really, really lucky in the students that we've had in my group. And then in addition to that, also had some research assistants. Pauline, when I started, she's still in the chemistry department. She helped me out at the beginning. Kelly Kilpin and Dr. Carl Schaffer, both of them came here for short research assistant positions before moving on to jobs elsewhere in chemistry. And then Henry down the bottom there is a current third year student. So there's my group currently. I think most of them are here. It's a glorious photo that we took the other day outside my periodic table that I've been trying to build on the wall in the chemistry department. And so these two here, Sam and Tristan, are current honours students. Dan, Quinn, James Finlay, Jaff and Rowan and Lynn are all current PhD students, although James is just graduating or will be next Saturday. And then Nat and Henry. And so that's my current group, and I thank them for all the things that they're doing at the moment. But I won't talk much about what they're doing because we haven't finished it. The other people have helped me out a lot, my collaborators, and as I said, synthetic chemists make stuff, and there's no point making stuff if it doesn't do anything that's interesting. And most of the time, we just do the making part, and then we need help to find out whether it's actually interesting. And so we have a lot of good collaborators. Many of them are just in the chemistry department. So Keith Gordon, who's the current head of department, and Lyle Hanton, who's our past head of department, both collaborate with my group. Associate Professor Nigel Lucas makes some fantastic organic materials that we are then joined together with our materials, and he's been a long-standing collaborator. Dave McMorrin, John McAdam, and Anna Garden all help within the chemistry department to make our science better, and so I thank them for all their help over the years. Outside of the chemistry department, but still within the university, I've got a number of biological or collaborators who help doing biological experiments. So Dr. Greg Giles in pharmacology and Associate Professor Heather Brooks in pathology, and then Joel Tyndall and Brian Monk have also helped us out over the years as well. And then outside of the university, all of these people, and these is not an exhaustive list, these are the people that we've got grants or had published papers with, but we collaborate with other people as well. But all of these people have helped our science out over the years, and so I thank them, because without them it wouldn't be as good as, well, it wouldn't be as nice as it is. And many funding agencies, somewhat to my surprise over the years, have decided to give us money. So we thank them as well. So what do we do? Well, we've got several major areas of research, but one of which is this click chemistry. And so click chemistry isn't our idea. It was developed by a number of people. It's an idea of doing synthesis in an easy kind of way, where you can bring two components or more together in high yield without having to do any purification, really. That's the idea behind it. So a bit like Lego in the molecular sense, nice straightforward reactions. One of those reactions is this one shown on the slide here. It's the reaction between an alkyne and an azide. And if you have a copper 1 catalyst, they will form this 1,2,3-triazole. And certainly before I started Otago, this was well known. It was first rediscovered, I guess, in 2001 by two different groups. Foken and Sharpless and Medal discovered this independently. And people used it to make polymers, make organic molecules, bring bioactive materials together. But one thing that we thought we could use it for that other people hadn't really touched on yet was to make ligands for metal complexes, which is what we do. And so these ones down the bottom, pyridine, bipyridine, and terpy, things that I used a lot of in my PhD and in my postdoc, very common nitrogen donor ligands that will bind to metal ions. And they're great, but they're difficult to functionalize sometimes. And more importantly, sometimes they're expensive to functionalize. You need to use sometimes palladium catalysis to make new ligands from these. So what we hope to do was to try and use click chemistry, because copper is very cheap and the chemistry is very robust, and we were very concerned when I started Otago that I'd never get any funding from anyone, and so we needed an inexpensive way to access our molecules. And so we thought, since no one else had been using these in coordination chemistry, maybe we could look at the fundamental chemistry behind that and see if they would coordinate metals and see if we could then make functional metal complexes using this approach. And so we developed a couple of, a method to making these ligands. And we chose a wide range of different functionalities to tack off the side, from biologically interesting functionality like steroids and sugars to just normal organic functionality, aryls and other things to tune both sterics and electronics and other components of the ligands. And so this one was meant to be BIPI-like, bidentate ligand, and these ones terpy-like, tridentate. And so you can access them from relatively cheap starting materials. Then we needed to know, would they bind metal ions? The other thing that we did, this is all one pot, and so if you're a synthetic chemist, these yields don't look that impressive. 50% is pretty terrible, 95 is much better, and sometimes we only got 50%, but that's because we're doing two reactions in one pot. We're making the azide, and then we're clicking onto the azide to make the triazole. And you say, well, why do you do it that way? Why don't you make the azide and isolate it? And the reason is, and this is the one wrinkle in this whole story, is that azides are explosive. And I didn't really want to destroy any undergraduates when I first got to Otago, so we developed methodologies using other people's ideas to make the azides in situ and then click onto them so that we didn't destroy any reaction flasks. And in this particular case, where there are only monoazides, it wasn't such a problem. But we also had this goal of making more complicated ligands, like shown here, and these are polyazides, and these are not a little bit explosive, these are very explosive, and so you don't want to isolate any of these. And so we're able to develop this methodology using other people's ideas to make these ligands, and that was our first goal. And then we're able to, these pictures that I keep flashing up, I want crystal structures, so they're molecular structures, this is what the molecules look like. And that's really the only data I'm going to show today. But so we're able to access these ligands, and then we had to look to see whether or not we could coordinate anything to them. And so we started with some pretty simple things, silver, palladium, and we took the monotriazoles just to see if they behave like pyridine. Now the chances are they weren't going to, because there's 2 nitrogens in these triazoles, there's only 1 nitrogen in pyridine, and perhaps unsurprisingly what we found was silver will bridge and form these bidentate metal complexes, which was not what we were hoping for. But in other metal ions like palladium, which is one of our favorite ions to use, metal ions to use, forms a pyridine-like complex and monodentate interaction. So they've got versatile coordination chemistry, which was nice from a chemistry standpoint. We're also able to show that if you methylate these triazoles, you can make these triazolidines, which are cationic, and then you can deprotonate them and make carbene-like, where the metal ion is bound through a carbon atom here and here to the metal ion, which is a different kind of way that these triazoles can form metal complexes, which is kind of cool as well. Now, that's great, that's new chemistry, that's stuff that no one had known before, and we're able to grow crystals of various different things, prove that we had the right thing. But really what I said at the beginning is that the whole point for making these compounds wasn't just to make new compounds, it's not what we're into, we wanted to find new properties. And so we were quite lucky. These gold complexes, related gold complexes are well known to be catalysts for organic transformations. And when I was a postdoc in Edinburgh, I had a colleague there, now Professor Eileen Lee, who's at Heriot-Watt University in the UK. We were postdocs together, and we met up at a conference, and she was looking for new gold catalysts. She was upset with the ones that you can buy from chemical suppliers. They weren't very good. They didn't do the things that she wanted them to. I said, oh, we've just made these new gold carbenes. You want to take a look at them? And so Eileen and Kelly and James Wright, who was a joint student with Nigel Lucas, made a family of these gold carbene complexes and studied their catalysis. And the upshot is that they are catalysts. They do a number of different normal gold transformations. Eileen showed that they're good catalysts. They're actually better than the commercially available ones. But what was disappointing was we made a family where we could change these 2 bits. We sterically and electronically altered them. James Wright did this, did a fantastic job. But none of that, making a library and having a whole series of catalysts to look at, actually improved the initial catalysis. And so they're good catalysts, but they're not great catalysts, which is a little bit disappointing. But it shows the versatility of these triazole compounds. And James, as I said, was a joint student with Nigel Lucas. And Nigel, as I said earlier, makes these fantastic carbon-rich materials. And so as part of that program, James made this fancy HBC linked triazole material. It's got this huge benzene-like, or super benzene, attached off the side, and just the crystal structure of this alone is a fantastic feat. And then James looked at the catalysis of these palladium compounds as well. We were hoping again that the large organic unit would allow these compounds to be recycled, but also to change the catalytic properties. Unfortunately, in this case, although these materials and the smaller materials are palladium catalysts for a very common Suzuki coupling reaction, they're not any particularly better than commercially available materials. So we can make new materials, and they are catalytically active, but not always better than what's known already. Then we got back onto trying to look at bidentate and tridentate materials, and we made a whole family of new materials based on these bidentate pyridyl triazole ligands. We needed to know how they would behave, and so they behaved in general how we would think. Take a metal ion that likes to form a square planar geometry, shown here. That's what you get with these ligands. Silver likes to form tetrahedral geometry. That's what you get with these ligands. Octahedral metal, you get 3 ligands around the metal, and they form, in this particular case, isomers, but they behave pretty much the same way that the BIPI ligands do. And so all the chemistry is like BIPI chemistry, but with this functionality off the side. And so then we started thinking, well, can we do something useful with these materials? And so that's when I was very lucky. Professor Keith Gordon has a group where they're interested in spectroscopy, emission spectroscopy, Raman spectroscopy. And so they, in collaboration with, this series of compounds in collaboration with Tae Kim, who was a 390 student, studied these rhenium complexes and found that they're emissive, which is what rhenium complexes tend to be. But interestingly, when we made a library of these, Tae built a library, we changed this R group out the side, we found that the emission properties don't change at all. And so that was interesting, disappointing initially, but interesting, because we were hoping by changing the group off the side, we would tune the emission properties, but it doesn't do that at all. And we found this is relatively common in these materials. You can change that R group off the side of the pyridyl triazole without changing the photophysical properties. Now, that might not be particularly useful for a lot of things, but in biology, and we haven't done this, but other people have run with this, you can therefore change the solubility of your emissive group, this rhenium, pyridyl triazole, change the solubility by putting something else out the side, or even target these materials by putting biologically targeting groups off them, and then use them as biological probes, emissions and emission spectroscopy. And so, even though we've not done it, our methodology has allowed other people to move in that direction. We have gone on and looked at other materials, photophysically active materials, and this is a compound that Jeff Wheel, is Jeff here? I can't see him, he is. Jeff made this when he was an honours student, and other people in our group have gone on to study these photoactive materials in conjunction with Professor Gordon's group. So that's one area where these materials are quite nice, quite interesting. The other area is actually for biological activity, and when I got here I knew very little about biology, but I was very lucky that a number of people have collaborated over the years with us. And so I went to another conference, and Professor Janice Aldrich-Wright, who's a long-standing interest in platinum anti-cancer agents, came up to me and said, oh, could you make us some platinum complexes and we'll screen the activity of those materials for you, because I think they could be really cool. And so we made these platinum complexes here. That's a platinum there, there's our ligand, and then Janice has these diamine units that she puts on the other side of these materials. And so we made, again, a family of pyridyl triazole complexes, because we can tune that R group using the click chemistry very easily. And we showed that all of those compounds have high activity. Many of them are more active than the well-known anti-cancer agent cisplatin. Unfortunately, and Dan helped out with this, and he's sitting there with his hat on, smiling away because he knows the story. Unfortunately, they're not more active, they're not selective for cancer cells, and that's a reoccurring theme in a lot of our work. We're able to make materials that kill cancer cells, but we don't have any selectivity yet, and so that's a work on. But these materials can be tuned due to the robustness of the click chemistry that we use to make them. And that brings me to this, which is all about antibacterial resistance. And so we've been really lucky because we have these compounds and we can tune their properties by changing the click chemistry. We got very optimistic, and we thought that we could use it to attack this antibacterial resistance problem. Now, obviously, antibacterial agents are very important. Bacteria cause a number of diseases, and we've had great antibacterial agents based on organic materials for a very long time. But the issue is that people misuse, don't take their whole course of the antibiotics, and bacteria just in general develop resistance by themselves. And so over the years we haven't been developing enough new antimicrobial agents, and so we've got now this resistance problem. And you can see here, these are all well-known organic antibacterial agents, and the starting point on the graph is when they were introduced to the market, and the other dot is when resistance occurred. And every single one of them, resistance develops, sometimes quicker, sometimes slower, but resistance develops in all cases because we never destroy all of the bacteria with these antibacterial agents. So really we need to be developing more and more antimicrobial agents as we go through. Now, as I said, all of these ones were purely organic, but there was some old literature and then some more recent literature that suggested that maybe metal complexes might be able to be antimicrobial. And we thought, given we have this click approach and we can make libraries of compounds, maybe we can add to this. And so some very nice work from a group in the UK. They developed this thing that looks a bit like some of our ligands, and they made metal complexes of it. They made iron complex, ruthenium complex, showed it will bind DNA. But more importantly, they had a paper where they measured its antimicrobial activity. Now, this is pretty rubbish. It's not very good, but it's active. And so we thought maybe we can get and into this and build on what they had shown, because we can change bits of our molecules, certainly the central spacer bit and various parts of our molecules, to improve the activity. And just as we were starting to do that, another group made a series of compounds where they did alter the central spacer bit, and they found more impressive activity. The lower that minimum inhibitory concentration is, the better. Those numbers are starting to get towards useful. So we thought maybe we could contribute to this. And also, my PhD supervisor, Bryce Bosnich, he worked for this guy, Dwyer, and back in 1952, Dwyer showed that ruthenium complexes with these phenanthrene ligands, or antimicrobial agents, actually had quite good activity. And because of the emergence of resistance, Richard Keane, who's an Australian chemist, started to re-look at those ruthenium complexes and found that some of the materials that Dwyer developed, and also these dimetallic materials, have good activity against a range of bacteria, including MRSA. So based on that, we thought we must be able to do something here with our click chemistry. I'll let the cat out of the bag and say that we haven't, but we tried. So we started with this, and this was with a PhD student that I had from India, Sridhar Vallis, so Shri. And he made this family of compounds where this unit looks a lot like the Hannan materials, but because we had the click approach, we could change the central spacer unit. We thought there's bound to find a more active material when we do this. And we didn't know too many biologists back then, but Joel Tyndall offered his help. He's a computational modeler mainly, but he offered to help calculate whether these materials would bind into DNA in silico. And also he knew Brian Monk, and so Joel and Brian had a student test these materials against not bacteria but a yeast. And the long story short is we made this vast library of materials, and not a single one of them was active against yeast or indeed bacteria when we went on and tested that. And that was a bit disappointing, and we were a bit puzzled by it all because they're very similar to the known compounds, but they're not at all active. So we had to fiddle around and try and trace the reason why they weren't active, and it turns out in our case that this pyridyl triazole motif is a little bit weaker donor, and so the ligands are just pulled off the ions, and therefore the compounds disintegrate before they get anywhere near the bacteria to show any activity. So we thought we could get around that. And the simple way to get around that is just to choose a different metal ion that's more inert or more stable in the sense of biological materials. And so we went to ruthenium, which of course had also been shown to be biologically active. But the problem with that is that if you go to ruthenium, it's harder to make these dimetallic materials. So Shri was able to make one compound, this one here, and there's the crystal structure of it. So we know we've made it. And luckily at this stage we had talked to Heather Brooks, and she helped us to test the antimicrobial activity of this material. It showed no activity against gram-positive bacteria, but it showed some, still not great, activity against common gram-negative bacteria, E. coli. So we thought we might be on the right track. So then we went and we looked at another series of inert metals. This takes cobalt, and this was work that was started by an old friend of mine from when I was a PhD, who came here to do a brief sabbatical, Mike Schramm, and it was finished off by Rowan, who's sitting up there. And then we tested these compounds. He made a small library of these cobalt compounds to test them against bacteria, and again, none of these materials were active. In this case, it wasn't because they decomposed. We were able to confirm that. We're not really sure exactly why, but other people in the literature suggest that the high charge, this is now 6+ charge, means that those compounds won't cross the bacterial membrane and get into the bacteria to show activity, which was kind of disappointing. So then most normal people would have given up at this stage, because clearly we're not very good at this biology, but not my group. So we decided we'd backtrack, and dimetallic wasn't any good. We'd go monometallic, and Shri started this work. He built a whole library of ruthenium-based systems that are a lot like the Dwyer and Keane systems, where we just changed the nature of the R group. And I think he made about 20 compounds, and 2 of them turned out to be active. But when you had a hit rate of almost none, that was pretty good. And so the 2 that turned out to be active were when the R group was a hexyl chain or an octyl chain. And those had pretty good activity, had MICs of about 8, which isn't terrible. And then when we screened them against Staph aureus, when we screened them against a wider variety of bacteria, they had even better activity against methicillin-resistant Staph aureus, about 1. Well, that seemed pretty good, but there was an issue with these materials that they're a mixture of isomers. We separated the isomers. It didn't matter which one we had. They're both active to the same level, but they're also chiral, and we couldn't separate out the enantiomers, and therefore we couldn't really pursue them any further, because can't give people chiral materials that aren't pure. So we thought we could get around that. We could just change the metal ion, use a different inert metal ion, see if we could get other compounds that are active. So we looked at rhenium again, because we made lots of rhenium compounds, and we found there, if they're neutral, so there's a chloride or a neutral ligand on the bottom of the rhenium, they're not active at all. If they're monocationic, 1+, then they have some activity, but they're not particularly active. Again, it was the ones with alkyl chains, hexyl chain, that were active, but the charge seems to be important to have activity in these compounds. So then we thought, well, we can get around the isomers by making a tridentate ligand, which we know how to do. And, or we can use a different metal ion, a platinum in this case, square planar metal ion, which gives us the same charge and inertness and a different shape. And both of those approaches work. Quinn and Dan and Sunurva, who's not here, but all contributed to making these materials. And the platinum compounds are active antimicrobial agents, as are these ruthenium bis tridentate compounds. But the bis tridentate ones are not as active as the platinum materials. And of course, at this stage, we thought we probably need to know something about how they work. So we did some preliminary biological mechanistic studies, and we found that these compounds here seem to permeabilize the cell membrane of the bacteria, at least in gram-positive bacteria. And that's a lot like what happens with these cationic surfactant materials. And maybe that wasn't a huge surprise. And we thought, well, okay, that makes sense. But what's a little bit puzzling to us at the moment, and this is an ongoing story, is that these materials, which are very similar and are cationic and have the same chain length dependence, it's the ones with 6, 7, and 8 chains that are really active, they don't seem to permeabilize the membrane in the same way. So they seem to have multiple modes of action. And the platinum compounds are even more interesting. They're the most active ones. They have a different shape. They're flat with chains off them, and we don't really know how they work at all. So this is an ongoing story, and that platinum stuff is unpublished as we try and piece together exactly how the compounds actually invoke their antimicrobial activity. But unfortunately, biology, I've discovered, is very expensive, and I have no funding to pursue the mechanistic study, so I need some grants in order to get this to move forward. If anyone wants to help, so that brings me to the second part of the talk, and the second part of the group, it's all metal-based chemistry again, and this is what's known as self-assembly, and again, this is an area of chemistry, and my wife's now giving me rolled eyes and yawning, that's good to know, is to make macrocycles and cages using metal ions. And the lability of the metal ions means that you can assemble these macrocyclical cage-like materials. You can do this with organic chemistry, but the metal ions allow us to do it at much higher yields. And a number of groups around the world do this, certainly not just my group. And the people shown at the bottom really developed this area. And the one person I want to point out is sitting over there, Dr. Dave McMorrin, who's putting his head down and pretending like he didn't do it. But this material here at the bottom is one of the most common approaches to making cage-like materials, and it's the approach that my group uses now as well. You can make these M2L4 cage materials. And Dave developed that when he was a postdoc at the University of Canterbury. And so you can use these cage materials to bind other molecules. That's why they're interesting. You can bind pollutants, you can bind reactive molecules. Here's white phosphorus. You can just bind random things because you feel like doing it. Look at their electronic properties. They're very versatile. They've got these cavities, and through supramolecular hydrogen bonding, other forces that are non-covalent, you can assemble things inside them. And you can even do catalysis. That's what this one here shows. So that's why we're interested in these materials. But what isn't shown there is that just as we started Atako, a group made a cage material that they bound a drug in, and it wasn't really a drug, but it was a drug-like molecule, and they showed that it would carry that molecule into cells. And so we thought maybe if we were clever, we could use one of these cages to bind a real drug, a known drug, and use that to deliver a drug molecule into cancer cells. And so the drug we chose was cisplatin, mainly because we're coordination chemists, and most anti-cancer drugs are organic, but cisplatin is a platinum anti-cancer drug. There's 3 that are well used, platinum drugs that are well used in the clinic, but cisplatin is probably one of the most famous. And the reason it's famous is it's one of the drugs that helped Lance Armstrong win 7 Tour de France's. One of the drugs, yeah. Anyway, we designed this cage based on some chemistry that we've been doing with these ligands, and we thought from molecular modelling that it would fit cisplatin in it, and it does, well, in the modelling at least. So we assembled this cage. It's easy to do, and there's an NMR there. I don't really want to talk about that. And we're able to show there's a crystal structure, so that's how we tell a lot of the times now. The NMR just confirms that the cage is intact in solution. But more importantly, the NMR also tells us that if we throw cisplatin in, that this peak here, which is that proton in there in the NMR spectrum, shifts and moves, and that means cisplatin binds inside this cage cavity, which was pretty exciting because cisplatin is said, actual drug. This was the first example of someone binding an actual drug inside a cage cavity. And then we're able to even more excitingly get a crystal structure to show how it binds, and we're somewhat surprised but also happy that we've actually found we've got 2 cisplatins bound within this cage cavity. It wasn't what we thought. The modelling looked like it would fit 1, but Jamie Lewis, who did this work, crystallised this material, has 2 cisplatins bound in the cage. So that was pretty cool. Jamie went on to show that we can also then release those cisplatins if we add a nucleophile, in this case either DMAP or chloride. DMAP not at all biologically relevant, but just shows that we can disassemble our cage. And chloride, which there is plenty of in the body, also disassembles the cage and allows us to release the cisplatin. And so that would be really cool, and I'd love to tell you that that works in actual biological media, but it doesn't. Those with eagle eyes will see that all of this was done in acetonitrile, which is most definitely not what our blood is made of. And so we needed to improve a few things. And the problem is the cisplatin itself was held into this cage through hydrogen bonding, and water is very good at hydrogen bonding. So we needed to improve the water solubility of this cage. We needed to make it more stable in the presence of biological nucleophiles, chloride being one, but many others as well. This cage rapidly disintegrates, and so although being able to release the cisplatin is important, we need to be able to do it on a timescale that actually is slower than what we currently had. And then also we need to enhance the host-guest interaction so the cisplatin doesn't just fall out when you put it in water. So my group spent a lot of time trying to do all of those things, and this summarises a lot of person hours in the lab building new materials, and unfortunately there's no good finish to this story, but I'm going to summarise some of it anyway because some of the people who did it are sitting here. We took the starting lead material and we made a whole bunch of different compounds by using our click chemistry. We could alter the properties of the cages, we could make them photophysically interesting. Keith Gordon's group again helped us to study those. We could make them redox active, but most importantly, eventually we could make them water soluble. And when we did that, cisplatin no longer bound in the cage cavity, which was a bit disappointing. It does still work in acetonitrile, as you can see here. This is a crystal structure. If you do the assembly and then do the binding of cisplatin and acetonitrile, it still works just fine. But in water, when we finally made the cages water soluble, it doesn't work at all, and that's because we're using hydrogen bonding to put the cisplatin in there, and so we've got a real problem. We're trying to fix that. We took an alternative approach to make these materials water soluble, thinking that maybe it was the triazole that was causing all the problems. So Dan put these PEG or ethylene glycol-like water solubilizing groups off the side of the cage, and he showed that we still make cages, and they still bind cisplatin and acetonitrile, but as soon as you put them in water again, no cisplatin binding, which is kind of disappointing, but that's the way it goes sometimes. That cage in its own right, though, we found another interesting property that led to a Marsden grant. We can switch that cage between cage and a macrocycle, and we could potentially then turn on and off catalysis, which is what the Marsden grant is about now. Something that we're trying to work with, so it's not all bad news, I guess. We then also took it, even though we were struggling with the binding, we looked at some other cage materials where we could try and improve some of the other properties. We were looking at trying to improve the stability of the cages, and so this is again work from Dan Preston, but also Rowan, who's there as well. They both looked at putting either electron donating groups off the cages or sterically blocking groups off the cages to try and improve the stability of these cages against biological nucleophiles. And in both cases that's successful. These cages are now much more stable against biological nucleophiles. We've even tested their anti-cancer activity, and they're actually active anti-cancer agents in their own right. But unfortunately, when you do this kind of material, you get this twisting of the cage. So even though they're more stable, now they no longer bind cisplatin at all. So that's kind of a bummer. And then also in an attempt to try and enhance the host-guest interaction and hold the cisplatin in more tightly, we altered these groups here, which are alkynes, to aryls, and then also to anthracenes, which are just even bigger aryls, and we're trying to fully enclose the cisplatin within the cage cavity. And that work was all done by Tae Kim in collaboration with Associate Professor Nigel Lucas. And we made a lot of nice cages that way, and none of those bind cisplatin either. So this is where the story in this particular case ends. It's all a bit disappointing, and we probably will never use any of these palladium cages to deliver cisplatin, unfortunately. But that doesn't mean that other people haven't had more success taking this cage approach and looking at different drugs. So having failed miserably to deliver any cisplatin to cancer cells, you start desperately looking for other applications that you can use the cages for. And so we were lucky again, I went to a conference and I met Associate Professor Brendan Abrams, who's a chemist at the University of Melbourne. He said, have you tried binding CO2 in your cages? Looks like it'll bind CO2 really well. I went, no, not tried binding. I don't know how. He said, oh, send them to me. We'll have a look at them. And so Dan made a series of cages. And these materials, surprisingly to us, but maybe not in hindsight, bind CO2 reasonably well. CO2, of course, is a greenhouse gas, so being able to bind it is kind of important. And it doesn't bind a lot, and palladium being very expensive probably suggests that it's not the best way to bind CO2 out of the atmosphere. Probably need something that's a bit cheaper, but it's a starting point. It shows the kind of things you need to design these materials. And so again, it's hydrogen bonding with the CO2 units. Calculations shown this. That allows us to suck the CO2 into the cage cavity. So it's a starting point for maybe looking at different applications. And another thing that, again, takes advantage of the hydrogen bonding array that these cages provide is this. It's what's known as a Diels order reaction. This is not work from my group, but we're now working with this group. So another old friend of mine, Paul Lusby, who was also a postdoc in the Lee group in Edinburgh when I was there, he discovered that our cage does this Diels order reaction. So Rowan's been to Paul's group a couple of times now, and we're starting to try and apply some of our cages to see if we can alter the Diels order reactivity in our materials. Probably shouldn't go on forever, but so Dan was able to show from some of the materials that we did make that we're able to do things that people hadn't been able to do before. So we wanted to use these cages for doing useful things. And one of the things that actually most cages that are developed in the literature are at the moment is they're made up of the 4 same ligands. And so what we found, because we have a family of ligands that we could look at, Dan looked at these different amino substituted ligands and showed that one of them, just the 2 amino one, could lead to heteroleptic cages that are made up of 2 different types of ligands, and that was the first time that people have been able to show this. Normally what happens is you either get a horrible mixture, as is shown in this cartoon, or you get self-sorting for one kind of ligand over the other because it's a better donor ligand. But when Dan took the 2 amino ligand, this one here, and titrated it in with our preformed cage, we made this kind of material. It's the first time that anyone was able to do that. And we weren't able to prove it initially. Dan did, and I've glossed completely over the horrendous amount of work that went into this, and Dan's smiling because he knows it's true. We weren't able to grow a crystal structure for a very long time, and so Keith Gordon group again helped us out. John Barnsley did a calculation that showed us that we were getting probably a cis orientation of all these ligands around the palladium, which is kind of cool. And the referees weren't happy with that, so then Dan did probably 1,000 titration experiments and NMR experiments to prove the cis orientation of the ligands, and we finally got it published because it was the first example of having 2 different ligands on a cage. And then, of course, as the way it always works, Dan was able to crystallize it to prove that indeed it had this cis orientation. Now, the reason that's interesting from a host-guest chemistry standpoint is now we can alter the actual cage cavity or the outside of the cage in a more fine-tuned kind of way. Before we had only high symmetry, either all pyridines or not pyridines. Here you can see in this one we've got pyridines and benzene groups, and by using this chemistry we hope to be able to do more specific molecular recognition kind of events. And then one thing that would be useful in drug delivery, but that is also very difficult to do, is to make big cages that bind lots of drugs. And so there are lots of people, and you can see some here, who have made very large cages, but none of these really hold on to guest molecules very well. And so we wanted to try and design some systems that we could bind multiple guest molecules in with the idea of doing drug delivery in the future. And we'd actually made something similar when I was a PhD student. Others have made these kinds of linear complexes where they have multiple cavities. And so Dan and Jamie Lewis took this challenge on, and they made these 2 ligands here and made these multi-cage assemblies where you've either got 2 cavities or 3 cavities joined together in these cages. Now, we're only able to crystallize one, but it's multi-cavity architecture. You can see it binds in the solid state gas molecules, but it's this one that's far more interesting because it's got a pyridine line cavity here and here, and a benzene line cavity there. And what Dan was able to show, and you don't have to go into the details of the data and how it shows you, but what Dan was able to show is that we can put cisplatin in the pyridine line cavities at the ends, and cisplatin will not go into the central cavity because it doesn't have the pyridine to hydrogen bond to. But what we can put in the central cavity is a different guest molecule. In this case, it's a pretty dull guest. It's triflate, which is a common anion. We can also put 2 triflates on the outside. And so in this new multi-cavity architecture, we're able to bind 2 different kinds of guests in different places selectively. Now again, in this particular case, the guests are not so exciting. Cisplatin is, but triflate's not. But it allows us to start thinking about, can we do a reaction in one cavity and then transfer that to the different cavity and do cascading type reactions using these multi-compartment host-guest compounds. And so we think that has great potential in the future. And so I've been whittling on for a very long time, and it's time to finish. And this is the last slide of my science. And this again is larger cavity cages that bind multiple guests. And so this is where we're going with a lot of this material. This is a big cage that binds these guests here. It shows interesting guest binding behavior in the sense that it'll bind guests when water is present, but not when it's not. And that's because you need the hydrophobic effect to drive these guests in. But the cage will bind multiple guests, and that opens up the possibility of bringing in two different kinds of guests and interacting together to do some kind of catalytic reaction. So that's where we're pushing forward now. And again, that was work jointly done with Nigel Lucas and by Tae Kim. And this to show that we can actually do some kind of catalytic reaction. This was an idea of Dan Preston's. Just when he was finishing his PhD, he brought together the two different parts of our research program, cages and triazoles, because why not? And he showed that if you take this ligand with a platinum here and use palladium, you can assemble these large sort of donut-shaped materials. Now, they're kind of cool in their own right if you're a sad synthetic chemist, but they're also kind of cool because these panels will interact with aromatic units. And one particular aromatic unit that it would bind was anthracene, and Dan was able to show that it will actually absorb light and photoactivate oxygen and turn that anthracene into this endoperoxide, and it does that catalytically. Now, I'd love to tell you that it's really good at that, but it's not. It does that for a little while, and then it decomposes because it's quite harsh reaction conditions, but it shows that not only can you do drug delivery and that kind of thing, but you can also think about using these cages as enzyme-like materials and do catalysis as well. And that's pretty much it. We make a lot of metal complexes. We try and do something useful with them. We use click approaches, we use cages, and sometimes if we're lucky, we get cool reactivity or biological activity. We'd certainly like it to be better, but that's a work on for the future, and we're not done yet, hopefully, so we'll keep going and keep practicing. Thanks again to all of my collaborators and all of my students and co-workers. You know, without them, I wouldn't have any of this to talk about. But there's also some other people I want to thank, because it's not all about the research that you do. Sometimes it's about learning how to do the job and learning how the university works, and I was really lucky there as well. I started, Professor Keith Hunter was the HOD, and he gave me my job, and so I'm very thankful to him and all of the things that he told me when I started out. Also thanks to Lyle, who was HOD after Keith, and definitely helped me learn how to be an academic, helped me with teaching, helped me with trying to do the right thing around the department, and Keith as well has been a great mentor, but also Dave Larson, who's sitting there and is in the office next door to me, taught me a lot about how to do teaching, both in lab and in lectures, and made me a far better a teacher than I was when I got here. And so thank you, Dave, and for all of the help that you've given me over the years. And then there are other people who were here when I started who also helped out getting the lay of the land. They're all now retired, but I thank all of them for their input early on in my career. We're very lucky in the chemistry department to have a number of excellent technicians, Ian and Jenny, and also at the moment China is helping out as well. And then we also have a fantastic glass blower, John Wells, who helped us out with materials that we needed in the lab when we started out, things that we couldn't access easily. We had excellent administration people. Unfortunately, they've both now moved on, but Teresa and Pip always helping us out in our admin team, and everyone else in the Department of Chemistry who've been there along the way. And also these people somewhat foolishly gave me their own money to help do some of our anti-cancer research. Charlotte Dobson is actually an 8-year-old, and she's the niece of Carla Maladandri, who's a lecturer or a senior lecturer in the chemistry department. Charlotte donated me $20 to do our anti-cancer work, and so that was very kind of her. Pauline Lane and Ocean Bridge donated us considerably more money to continue that kind of work, which was very kind of them. And then most importantly, these people, over the years, my mum and dad who are up there have supported me, even though Dad's probably still not forgiven that I quit law. Hopefully thinks that it didn't work out too badly. And my sister, who's not here, Emma, has also been there for a long time for me. And then my wife and my children who put up with me going away to conferences, especially my children put up with me going away to conferences when their birthdays are, because Northern Hemisphere conferences are on when their birthdays are, and I have to bring back very large presents to say sorry. So thank you to them as well. Thank you.
Thanks very much, James. My name's Keith Gordon. I'm the HOD of Chemistry. I'm just going to give a vote of thanks. And it's just amazing what James has done. I mean, I think what I was thinking, I was writing down some notes. I thought there were two things sprung to mind. One was nano Lego, which I quite like the idea of. I think chemistry, especially the ability to make materials, is a really cool thing that chemistry can do that frankly no other subject can do. It's as simple as that. So that's kind of cool. But I think James's talk really showed that, oh please, getting nature to do it for you doesn't count. One of the interesting things I think that James talked about a little bit was actually his interaction with Jim Johnson, because it really reminded me that Jim, I know Jim Johnson quite well, as James does, and Jim's a very applied scientist. And although much of what really drives James's research is quite, is fundamental, one can always see him look to try and engage with other areas and enable other sciences with the innovative work that he's done. And I think in looking at what he's done, I think the first thing is he's remarkably, almost ridiculously modest about how difficult some of these things are to make. I mean, and it's of course, for those of us who study materials, you can't make solar cells or photocatalysts without new materials. You can't make mobile phones without new materials. So the ability to make new materials that have new properties is incredibly important. And I think James sort of took us through that entire area, and it was very nice to see his frugal nature in the use of the click reaction using copper-1 chemistry. Although generally, as HOD of Chemistry, I don't like to use the word explosive, also because of my accent. I don't like to use the word explosion either. We like to call them very reactive materials. And James, of course, has demonstrated beautifully click chemistry, incredibly powerful methodology in developing new catalysts and then working with collaborators to show that. And then in developing the bidentate bidentate ligands to make complexes that he did, he really kind of stumbled upon something I think he's being far too modest about, and that is the ability to make a compound that has one property here, and then when you fiddle with it over here, it doesn't screw everything up. That's actually really, those of you who don't know any chemistry, that is really difficult, really, really difficult to do. So it's fantastic that he was able to use that sort of tune, if you like, tune the nano Lego over here while not interfering with the properties that were quite important. I think also in the story of James's antimicrobial work, I mean, this is the first lesson I was ever taught by a postdoc when I started was that the first lesson of research is disappointment. And there's obviously a lot of disappointment in that work, but it also really demonstrates the determination of James and his research group to just keep digging away until we find something useful. And in that case, they were able to show, indeed, they were able to show that, sure, their initial compounds didn't work, but then when they went back and tried these other ruthenium compounds, they actually are on the cusp, potentially, of finding a new way in which the metal complexes are going to disable bacteria. And then in the final part, the self-assembly. So the self-assembly is rather like you just ask the nano Lego if it could fit itself together and you don't really do anything. That sounds awfully easy, but I think there's a little bit more to it than that. But that's a wonderful way to actually create molecular encapsulants. So you can, obviously the target was to look at cisplatin, and that, again, an awful lot of work. A lot of things didn't work. But then, of course, discovering that you could switch between a macrocycle and a cage and therefore switch on and switch off catalysis. And then, of course, well, you don't have to encapsulate cisplatin. You can try CO2. And you can encapsulate reagents so that you can actually facilitate things like the Diels-Alder reaction. So I think that, and then, of course, in the final part, that ability to make heteroleptic cages, the idea that now you're not just asking the Lego to self-assemble, but you're asking certain colored Lego to assemble on this side and a different color to assemble on that side. I mean, that's a remarkable breakthrough in terms of how that self-assembly works and really offers materials which effectively have different faces that have different properties. So it's an incredible, I think, story through a whole series of really quite difficult and challenging chemistry and a real, I think, not only fantastically innovative thinking, but such sheer determination to get it to work or get something useful out of it by reaching out across science and across with other scientists to make the most of what is really very clever fundamental chemistry. So let me just finish by we show our appreciation for James, and I think I'm going to give him a gift now. Yes, and if James can come up, I will give him a gift while you applaud.